Welcome back. In this video, we're going to look at what is comparative statics, a method that helps us analyze the equilibrium when different factors move around. First, we're going to introduce the notion of comparative statics, and then we're going to see how it works through our example of the process pork study. If we think about the market equilibrium problem we've been dealing with so far, there are things that are given to the model, and there are things that the model told us. So what we've put into the model are a demand curve, a supply curve, and then in addition to them, we impose something called equilibrium. We explicitly described what we mean by something called equilibrium. And then once we have these pieces in place, the model gave us back a pair of very special price and quantities such that demand is equal to supply at the same price. And these notions are critical because in any model economics, typically what's going to happen is we're going to impose something into the structure of the model. And then the model is going to feed back something to us. And it is very useful to make a distinction between the objects that we put in and the objects we get in return from the model as a result. Think of an example where you have an air conditioning unit and an open window. On the one hand, we can decide how much we crank up the air conditioning unit to lower the temperature in the room. On the other hand, we can decide how much we want to open up the window to let the air circulate. And the overall temperature in the room is going to be a result of our settings, but it will be worked out by these two objects simultaneously. And the temperature in the room is going to be the feedback to us from the room or from the system. In other words, we're going to tell the model in the context of the market equilibrium what is demand, what is supply, and what we mean by an equilibrium. And then the model is going to tell us what the equilibrium is. More specifically, in the model we just looked at, we imposed what is the price of beef, price of chicken, and the income level, which then help us pin down the demand curve. We also imposed what is the price of hogs, which is the input that affects the supply function. Once we have these parameters in place, we pin down a demand curve and a supply curve. And then we put them together and require that the quantities have to be identical at the same price. And then we manage to solve the problem and find this particular equilibrium. But that's what the model is telling us, as opposed to something we imposed very directly into the model. In other words, we actually built from the demands and supply functions towards this equilibrium outcome, following a couple of different steps. First of all, we imposed what are the values of these blue variables. These are the things we feed into the model. We did not directly impose what are the prices or the quantities. Now, with these specific values for the blue variables, we end up with these simpler demand and supply functions, which we can then plot. But we still don't have the same quantity in both the demand and the supply. To get that, we impose the equilibrium definition, saying that we want the same quantity output from both functions at the same price level P star. And that equilibrium definition then gives us back this pair of price and quantity as our equilibrium. Most frequently, what we really care about in a problem of analysis isn't really where the equilibrium is necessarily, but in many cases, we're more interested in how would the equilibrium change when the environment changes. For instance, if the price of beef increased by a little bit, or the income level decreased by a little bit, how is that going to change the equilibrium price and the equilibrium quantity? Well, to do that, in this context, what we're really asking is, what if these blue variables changed a little bit? How will the equilibrium objects, P star and Q star, move around as a response to the changes in the blue variables? And comparative statics is exactly the type of tool in economics that help us answer this type of questions. Perhaps you might say that, well, I know how to solve that problem. Let me change the price of beef from $4 to $5 and then plug in all these values again into the blue spaces. And then we resolve the problem and get a different equilibrium. Then we can compare the new equilibrium to old equilibrium. And then that will tell us how the equilibrium responds to a $1 increase in price of beef. But that seems awfully cumbersome. And what if some other variables changed? Then you will have to resolve again. And what if the value isn't increased from 4 to 5, but instead from 6 to 7? How do you know the effect will be the same? Well, it turns out there's a much easier way to carry out this analysis, and this tool is being called comparative statics. Now let's see how it works. The essential idea of comparative statics in a more general way is the following. In any kind of economic model we build, there will be variables that we feed into the system that determines what the model is. And then the model will work itself out and give us some kind of feedback that describes what the state of the model is. The variables we feed into the system are being called exogenous variables. These are things that are determined outside of the system, external to the system. Whereas the objects that are determined within the model by the model itself, through interaction of different parts of the model, are called endogenous variables. They are generated within the system. In general, a comparative statics analysis is to analyze how the endogenous variables respond to the exogenous variables. And this technique applies beyond the market equilibrium model in many, many different economics models, and is a very, very useful tool. In the context of the demand and supply analysis we've done, what happens is, for a demand function, we plugged in these exogenous variables, and price, which is endogenous variable, but it plays a part in the demand function. Similarly, for the supply function, the exogenous variable will be the price of input, and the endogenous variables will be the price and quantity supplied. Now, what we've done in the equilibrium is that we imposed that the quantity demanded has to be the same as quantity supplied at the same price level P star. And we called that particular quantity the equilibrium quantity Q star. So Q star and P star are the endogenous variables that are determined within the system. And by solving the system of demand and supply, we get our equilibrium outcomes as functions of all these things we feed into the system. In the previous example, because we plugged in specific values for all the blue variables, they disappeared. Everything collapsed into a number. So we're no longer able to keep track of them. But they are, in fact, playing a part in determining the equilibrium price and equilibrium quantity. The exercise of comparative statics is to ask that if we change any one of these exogenous variables, how will they change the equilibrium objects, the endogenous variables, the equilibrium price, and the equilibrium quantity? So coming up, we will see how comparative statics works through a more general approach of solving for equilibrium, and we'll see how this approach will provide us with a more precise answer about the analysis of equilibrium behavior comparing to a graphical approach that we're familiar with from the principles classes. Now we're going to try to solve for the equilibrium from a slightly more general approach by using the demand and supply functions without imposing specific values on the exogenous variables. Throughout this example, I'm going to mark all the exogenous variables blue and all the endogenous variables red. So the step one, just like our example before, is that we're just going to impose the equilibrium definition. And that is just saying that we want the quantity demanded to be the same as quantity supplied at the same price level. Now, once we write down this equilibrium definition, we can just plug in these demand and supply functions from what we have here. We can write down demand function on the left-hand side of this equation, and we can write a supply function on the right-hand side of this equation. And both sides are a function of P star. So we can collect P star, the only endogenous variable, on one side of the equation, and then put all the blue variables and constants to the other side of the equation. Think of the blue variables as parameters and the red variables as unknown. And we can just solve that. So as a result, we're going to find that the equilibrium price is equal to this particular expression. Before we rush to find the equilibrium quantity by plugging in the equilibrium price into either demand and supply like we've done before, now let's take a pause here to analyze this object a little bit and understand how the equilibrium price would change or respond to the changes in these exogenous variables. It turns out the analysis is particularly simple if you start to use the tools of calculus, because we recognize that the equilibrium price is just a function of PB, PK, and pH. To understand how $1 increase in the price of beef will change the equilibrium price while all the other things are held constant, we can just take a derivative of the equilibrium price with respect to the price of beef. And as a result, because we're holding price of chicken, income level, and price of hogs constant, the only thing that changes in this expression is only here. So the derivative is only 1/3. The interpretation of this result is the following. If there is a $1 increase in the price of beef, the market equilibrium price for processed pork is going to increase by 1/3 of a dollar. Isn't that convenient? Similarly, you can calculate the effect coming from $1 increase in price of chicken, the increase in income for consumers, or an increase in the price of hogs. And now we'll turn to look at the effect on the equilibrium quantity as opposed to equilibrium price. It turns out that there are at least two different ways we can analyze the effect on the equilibrium quantity. The first way is the more intuitive way, where we just plug in the equilibrium price into either one of these expressions, the demand function or the supply function, and then calculate what is the equilibrium quantity. From there, we just repeat the exercise we've just done before. You take a derivative of the equilibrium quantity with respect to any one of these exogenous variables to get the effect. But it turns out, algebraically, that is not always the most convenient approach. And in more general problems, sometimes that is not even the most appealing approach at all. Instead, I'm going to introduce you to a more sophisticated method, which seems a little bit more cumbersome at first, and is difficult to wrap our heads around. However, I think by thinking through this problem in this route, it actually teaches us a little bit more economic intuition. So now let's see how it works. This particular approach will rely on the use of chain rule in calculus. And as an example, we're going to look at how the change in the price of beef changed the equilibrium quantity. To carry out this exercise, we need to keep in mind that the equilibrium price is in fact a function of price of beef, price of chicken, income level, and price of hogs. What we're going to do is that we're going to directly take derivative of the equilibrium quantity without plugging in the equilibrium price. And we'll see how this works. In particular, on this slide, we're going to demonstrate how it works if we take a derivative of the quantity supplied with respect to the price of beef. First of all, quantity supplied is a function of price and price of hogs. When we plug in a particular equilibrium price here, what we will get as the outcome of the supply function is going to be the equilibrium supply. So now we're going to use exactly this expression down here. And the only difference is that we're going to replace P, which is any price, with a particular price that is the equilibrium price here, P star. Now if we take a derivative of this particular expression with respect to PB, what's the result? Well, let's think about this a little bit. One answer might be that PB does not appear here, so the derivative is going to be 0. However, that is not necessarily true, because when PB changes, well, we know pH doesn't change. It's just something that would feed into the model while holding that constant as we think through this analysis. However, when PB changes, the equilibrium price will change. And that's why this fact is very important. We need to remember that when price of beef changes, the equilibrium price level will react. In fact, that's our whole point in the previous slide. We just showed that when there's $1 increase in price of beef, the equilibrium price will increase by 1/3 of a dollar. Now, once we come back to this expression, what happens is when we take the derivative of this expression with respect to PB, the constant will not change. The price of hogs will not change. However, the equilibrium price will respond. So through the chain rule, what we're saying is the price of beef will change the equilibrium price. And when the equilibrium price changes, the quantity of supply will change. More specifically, by chain rule, quantity of supply is a function of equilibrium price, and equilibrium price is in turn a function of price of beef. So when we take derivative of quantity supply with respect to price of beef, we need to use the chain rule. And the result is a product of two pieces. The second term in this product says, when I increase price of beef by $1, how much will the equilibrium price change? Well, we already know that from the previous calculation, which is a third of $1. Now, when there's $1 increase in the equilibrium price, how much will quantity supply change? Well, that's straightforward. It's just a derivative of this expression with respect to P star, and that is 40. In other words, the total effect coming from $1 increase in the price of beef is going to be the compound of these two layers of effects. The increase in price of beef by $1 increases the equilibrium price by a third of $1. And because every dollar increase in price of the processed pork is going to change the quantity supplied by 40 units, so 1/3 units of increase is going to change the quantity supplied by 1/3 of 40. And that is our result. The interpretation is straightforward. What our result says is that following a $1 increase in the price of beef, the equilibrium quantity is going to increase by 1/3 of 40. Thinking through the problem like this might not be the most intuitive at first, but as you think through the problem by using chain rule, it really helps us highlight the mechanisms through which the effect passes through the system. In other words, what it says is changes in price of beef moves the equilibrium price, and the equilibrium price then in turn changes the quantity of supply. Well, now let me make a couple of remarks. First of all, you might say, gosh, this is really difficult and counterintuitive. Why don't I just plug in P star into supply function or demand function and then get expression of Q as an expression of all these different exogenous variables and then take derivative from there? You can certainly do that, and if you've done it correctly, you'll get exactly the same answer. In fact, you should definitely try this, and what you realize is that algebra involved is very cumbersome and sometimes really easy to make a mistake in them. And in addition, you just won't be able to get the intuitions we just observed that shows us this layered effect passing through from one level to the next. You might look at the analysis we've just done and then ask the question, why do you pick the supply function as opposed to the demand function? Well, my answer is that it really doesn't matter for the end result, because in the equilibrium quantity is the same coming from demand or supply as long as you use the equilibrium price. However, there is an added level of simplicity if we use the supply function. And the reason is that if you look at the supply function here, price of beef does not move supply function itself. The only way that transmits into the equilibrium quantity is by moving the equilibrium price. However, if you look at the demand function and you try to change price of beef, it's going to affect the quantity through two different channels. First, it's going to change the equilibrium price as we just discussed. But on top of that, it's going to shift the demand curve by changing PB. And now let me show you technically how these two channels translates into an expression. Suppose now instead of using the supply function to do this analysis, we want to use the demand function. What's going to happen? Well, we do exactly the same thing. We're going to take a derivative of quantity demanded with respect to the price of beef. And we recognize that quantity demanded in the demand function is determined by the equilibrium price, PB, PK, and Y. Now we can just plug in our demand function like this. Now if we take derivative of this expression with respect to PB, two things will change. Well, 171 won't change. PK and Y will not change because we're fixing them as our exogenous variables. But now, as PB changes, P star will change for exactly the same reason we described on the previous slide. Because the equilibrium price is going to move around when price of beef changes by $0.33 every time PB increases by $1. But in addition, when PB moves, demand will change even the price does not change at all. And that's the lesson we learned in the previous part when we look at this demand function. When PB increases by 1 unit, quantity demanded is just going to change by 20 units without the price changing at all. Now, what it means is the derivative is now going to have two parts. The intuition here is just that the overall effect is going to be these two effects combined together. The first effect is a chain rule type of result that we've done before. In other words, price of beef changes price in the equilibrium, and the equilibrium price changes quantity demanded. The second effect is a direct impact from price of beef on quantity demanded through the demand function itself. Those of you who pay close attention to the notations will realize that I'm not using partial derivatives here, but instead I'm using partial derivatives here. By using partial derivatives in the second expression, here I'm saying that I'm changing PB without changing any other things, including P star. So now, looking at the combined results, what we have is the following. When equilibrium price increases by $1, quantity demanded will drop by 20 units. And that's moderated by the effect of PB on the equilibrium price, which we know is $0.33. But that's only the first channel. Well, the second channel is coming from the direct effect of price of beef on the equilibrium quantity through demand function, and that is 20 units. Whenever price of beef increased by $1, quantity demanded increased by 20 units. And the overall effect is the combination of these two channels together, and that is 40/3. Exactly the same result that we've gotten from the supply function. So although this is a slightly longer route of getting the answer, I do think there is some lessons to be learned from it. So intuitively, how do we think about these two different routes? Well, here's the idea. If we look at a demand and supply curve, what happens is that when the price of beef increases by 1 unit, our demand function shifts to the right. Now, if you look at the equilibrium price increased by 1/3 of a unit. Our first analysis of taking derivative of the supply function with respect to PB is to keep track of the change in quantity by focusing on the supply curve itself. So when P increased by 1/3, we know Q increases by this much along a supply curve, and that's going to be 1/3 of 40. However, our second approach of taking a derivative with respect to the demand function really combines two different things. First of all, as price of beef increase, we know that the demand function is going to shift out like this. So at the same price as before, the quantity is going to increase by 20 units. And that's this effect here. That's saying the quantity of demand will change even without a change in the equilibrium price. The second effect is that even if we do not shift out the demand curve, but only raises the equilibrium price, then what's going to change is that our demand is actually going to fall back. And that is our first expression here. So what is the overall effect? Well, it is the combination of the shifting of the demand curve outwards and the shifting back in quantity demanded when the price increases. And that gives us this overall effect that changes quantity from here to here. Because on the graph, what you will see is demand curve shifts out by this much when PB increases. But then, as the equilibrium price increases, the quantity shifts back to this particular equilibrium quantity. So on the net, the quantity of demand only increases by 1/3 of 40 units. Through more and more examples in this course, hopefully you will start to see this repeated idea that the analysis through algebra typically get us very far in the analysis. And then it complements really well with the observations in graphs that affords us with richer intuitions. And it is really by comparing the algebraic solution to the graphical solution and back and forth that we learn a lot of insights from these models. And as the last remark, I want to remind you that it doesn't matter which route you take, taking derivative of the demand function or the supply function with respect to the exogenous variables, you should always keep in mind that equilibrium price is by itself a function of exogenous variables. And that is the key element in these analyses. In principal classes, we have already done comparative statics without you probably knowing it. And the way you've done it is through the graphs. If you remember, in any kind of graphical analysis, when price of beef increases, demand curve shifts out, and then we know equilibrium price goes up, equilibrium quantity goes out. But that's about it. We're almost never able to get such a deep insight into the problem and into how the model moves around as the one we've just gotten by going through the algebraic analysis. To reiterate my message on using functions in economic analysis, by using the algebraic solutions and analysis, we're able to draw much richer results and insights from the models than we could otherwise do with the graphs alone. So it is actually a cost worth paying, although it might seem a little bit intimidating at first.